Well, thank you for joining us, okay, for this presentation with a lively discussion, I hope so. Since in my last update information, we had around 70 registrations. In this free webinar, the speakers will explore the potential for energy recovery in water networks. And it is my great pleasure to give my contribution to support this series of webinars launched under the REDAWN project. In this event, we demonstrate the great potential for micro-hydropower in water industry to generate clean energy and contribute to improving the sustainability of water sector. Using a series of case studies in water distribution and irrigation networks, the significant economic and environmental benefits of micro-hydropower implementation will be explored. Okay, Charlotte, please. Next slide.
Good afternoon, everyone. It is my pleasure to welcome you to the third of the three webinar series on energy recovery potential, economic, social, and environmental impacts. I am Helena Ramos, one of the REDAWN project partners based at the Instituto Superior Técnico, the IST, in Lisbon, the engineering faculty of the University of Lisbon, Portugal. This webinar series is organized and endorsed by REDAWN project, which means reducing energy dependency in Atlantic area water networks. The REDAWN project is part funded by the Interreg Area Program through the European Regions Development Fund. The map of the countries and regions covered by this funding program are shown in the right part of this slide. In water supply systems, in particular distribution and in-transmission pipelines, turn them as potential energy sources. The evaluation of the power available in these pipelines can define the economic benefits of converting energy dissipation into energy production. The project is being delivered by a consortium of 15 partners and valued associated partners from 5 countries along the European Union Atlantic area coast, including also our external partner in Italy as a leading expert in micro-hydropower. The water system efficiency and the energy recovery potential in a water energy nexus come through the implementation of suitable pressure control and energy recovery devices, such as pump turbines, providing guidelines for the determination of the most technical, cost-effective solution. Integrated analysis of water and energy allows more reliable, flexible, and sustainable eco-design projects, reaching better resilience systems through sustainable new concepts. Due to the potential of hydropower in the water sector, several investigations have focused on the evaluation of the installation of these devices in water networks, showing that up to 40% of the gross power potential available in a pressure-reducing valve could be recovered by replacing or coupling the pressure-reducing valve by or with a pump as a turbine. In water systems, in particular in transmission pipelines, the hydraulic power is significant and relatively constant, turning these pipelines in potential energy sources. The knowledge of power availability is an essential factor to predict and define the economic benefits of converting energy dissipation into energy production. The reduction of water losses, a certain part of this energy in the network can be recovered, reducing greenhouse gas emissions and making the water supply system more efficient and sustainable. Pressure-reducing valves, PRVs, are a convenient device for reducing leakage by pressure control. However, the energy dissipation that takes place in a PRV is wasteful of energy resources, and this energy could be recovered by substituting or putting in series the PRV with a micro turbine. Micro-hydropower implementation can lead to more sustainable water service, allowing to reduce financial losses, enabling innovative business models to serve better the urban and rural populations. Water abstraction and distribution are among the activities in which the energy recovery plays an important role. In the European Union, 8% of the total energy consumption in recent years was related to the water supply. In addition, it is estimated that 32 billion cubic meters per year, around 60% of the treated water, are lost in the water distribution process globally. This is mainly due to the excess of pressure, the aging of infrastructures, the non-optimal design, and the increase in water stress in urban and irrigation areas. In this slide, on the top, we can see examples of pilot demonstration sites already developed in the REDAWN project. On the left, an implementation in an irrigation system, in the middle, an implementation in a drinking system, and on the right, an implementation using a process industry system. Today's seminar will focus on the energy recovery potential and associated impacts. The first talk will present an overview of the energy potential evaluation applied to the water sector, and the second one will present an overview regarding environmental, economical, and social associated impact. Before I introduce our speakers, please note that this webinar will be in listen mode only until we get to the Q&A discussion part. This will help to minimize disruptions and keep to time. Please use the chat function to type your questions and comments. We will aim to address most of them after the presentations. Please start with your name and affiliation. Please be aware that this webinar is being recorded.
Okay, now I have the pleasure to introduce our speakers. Okay, the first speakers will be Aida Mérida Garcia. She comes from Córdoba, Spain. She has the PhD in agriculture, food, forestry, and sustainable rural development engineering at the University of Córdoba in Spain. During her PhD, she spent several months in Trinity College Dublin, Department of Civil, Structural and Environmental Engineering. And currently, she works with the energy recovery potential from micro-hydropower in the water distribution networks. She has focused on the optimization of the water and energy use in water distribution networks, including the integration of renewable energies and the assessment of the environmental impacts. Our presentation will focus on micro-hydropower energy recovery potential in water distribution networks in the European Union Atlantic area. The second speaker will be Indalecio González Fernández from Jaén, Asturias. Indalecio González Fernández is engineering of energy by the University of Oviedo and has the MBA in technology management. He has been teacher in the University of Oviedo and is in masters and training courses in renewable energies. He is working as head of renewable energy department and energy planning of the Regional Energy Agency and manager of the Regional Energy Cluster of Asturias. He will present results about economic and environmental benefits of the micro-hydro plants in water networks. Okay, now I give the word to Aida Mérida to make her presentation.
Hi all, my name is Aida and I'm working as postdoctoral researcher in Trinity College Dublin. Today, I'm going to show you a summary of the final results obtained for the micro-hydropower energy recovery potential assessment in the water industry in the European Atlantic region. This work has been developed under the Work Package 4 of the REDAWN project. The objective of this work package focused on the assessment of the potential for micro-hydropower energy recovery in the water sector, including drinking water, wastewater, industry, and irrigation networks across the countries included in the Atlantic area of Europe. The work was organized in these four main steps. The first one was the data acquisition, which was gathered by the different partners in each region for the four sectors: drinking water, wastewater, irrigation, and private industry. Then, the following step was to estimate the potential for energy recovery based on flow and pressure data at the identified sites for the different countries and sectors. The energy recovery potential for micro-hydropower was estimated by this equation, and considering only those cases in which this potential was higher than 2 kilowatts of power, as plants with a lower power are usually not economically viable. The variability in the frequency of the recorded data forced the selection of annual average flow and pressure values as the most appropriate for carrying out this assessment. Then, based on these results, the potential for energy recovery was extrapolated at a country level for the entire region analyzed, adapting the methodology to each sector. Starting with the drinking water sector, the initial information composed a full database for Scotland, Wales, and Northern Ireland, a partial database for Ireland, Spain, and Portugal, having no information for France and England. In the case of France, 2 sites were studied, but the potential found was minimum power. From the calculations of the sites collected, it was determined a ratio based on the power potential and the corresponding population served by the networks. Due to the differences between the individual ratios, as the ratio for Scotland was 4.28, significantly higher than the rest of the countries, as for example 0.09 for Spain, kilowatts per 1,000 people, the extrapolation was designed under 4 possible assumptions, considering these individual ratios, an average of all of them, a partial average for all countries but excluding Scotland, and the median. The first assumption used individual ratios for countries with full database and the total average ratio for the rest of the countries. Assumption 2 used individual ratios for all countries, so France and England have no results for this scenario. Assumption 3 consider individual ratios for countries with full database, while use a partial average for countries with partial or no database. And finally, assumption 4 consider the median of the individual ratios for all the countries. Once the 4 assumptions were defined, the extrapolation for the drinking water sector was made considering the total population of the different countries. In the case of the wastewater sector, the extrapolation for the total population considered the linear correlation found between the micro-hydropower potential and the population served by the analyzed networks in Ireland and Spain. In the case of the irrigation sector, the extrapolation was based on the micro-hydropower potential found in the analyzed networks and the corresponding covered surface, as well as the regional information about the irrigated surface for the south of Portugal. In the case of Spain, the extrapolation considered, in addition to the covered surface and the estimated micro-hydropower potential of the analyzed sites, the ratio between the surface and the total water irrigation volumes and the localized irrigation surface for all the country. Finally, for the industry sector, the initial information came from some sites located in 1 and 3 private industries in Ireland, respectively. But in the case of Spain, the discharge volume of private industries for around the 80% of the country area were analyzed. For this reason, the ratio energy recovery potential to population obtained for Spain was then used to extrapolate the results to the rest of the countries. Moreover, it was also considered the importance of the industry activity in the gross domestic product in each country. And finally, once the extrapolation of the results was finished, an estimation of the future resource projections was made, based on the population growth estimations for 2030 and 2050. Starting with the results, here in this table, it is shown a summary of the total number of potential sites identified for the different sectors and countries. It is important to note that the drinking water sector was the one with the highest representation, with 87% of the total identified sites, from which 99% corresponded to the UK, in which an important part was from Scotland. The results obtained from the energy research assessment at the identified sites are summarized in this other table. Thus, from flow and pressure records at the different sites, it was estimated the power potential for micro-hydropower, resulting in a total of 31 megawatts of power, which translates to an approximate value of 254 gigawatts-hour of energy, considering 24/7 as operation time for all the sectors except for the irrigation sector. In the right side, it is shown the contribution of the different sectors and countries to this total, with the drinking water sector as the one with the highest contribution with 81% of the total. For the resource extrapolation, under the 4 assumptions defined before, the results were the ones shown in these tables. Thus, the total extrapolated energy for the drinking water sector ranged between 299 and 1,760 gigawatts-hour if all assumptions are considered. However, if assumption 2 is not considered, as England and France are not represented, the minimum of the range was set at 559.3 gigawatts-hour. In the case of the wastewater sector, the total energy extrapolated amounted to a total of 75 gigawatts-hour, with France, England, and Spain as the countries with the highest contribution. The results of the extrapolation for the irrigation sector are shown in these 2 tables. Portugal in the left, with a total energy potential of 24 gigawatts-hour, and Spain in the right side, with a total of 221 gigawatts-hour. And finally, the results for the industry sector show with a total micro-hydropower energy potential of 47 gigawatts-hour. The total resource extrapolation expressed in terms of energy is summarized in this table and also displayed on the color map with a total ranging between 926 and 2,127 gigawatts-hour. Regarding the future projections, it was considered the future scenario of population for 2030 and 2050. In that way, all the extrapolation process was then repeated to evaluate the results for the different countries and sectors with the expected population provided by Eurostat statistics. Thus, the research projections showed an increase between 3.6% and 4.2% for 2030 and between 7% and 8.7% for 2050. To finish, as conclusions, for the data acquisition stage, the drinking water sector presented a high volume of data of potential sites, most of them coming from Scotland. In the case of the wastewater sector, only information from Ireland and Spain was available. For the irrigation sector, 18 representative irrigation networks in Spain and Portugal were analyzed, and in the private industry, the initial information corresponded to some sites located in 4 private industries in Ireland and Portugal, while in the case of Spain, the discharge volumes were available for most of the country area. For the extrapolation stage, the methodology was based on the total population of the country and the micro-hydropower potential to population served for each country, considering 4 different assumptions due to the differences between countries. For the wastewater sector, the extrapolation to the total country population was made considering the linear correlation found between the micro-hydropower potential and the population served in the analyzed networks in Ireland and Spain. For the irrigation sector, the extrapolation was applied to the south of Portugal and Spain, areas with similar irrigation networks to those analyzed, showing this sector a significant potential in those areas in which the agriculture activity plays an important role. In the case of the industry sector, the extrapolation was based on the results obtained from the analysis of the discharge volumes in Spain, considering also the importance of the industry activity in the gross domestic product of each country. Here, it was also observed that the internal analysis of private industries could increase this potential, taking advantage of the excess of pressure of the networks. From the total extrapolated results, Spain represented 50% of the power potential, followed by the UK and France, with 21% each, while in terms of energy, Spain represented between 30 to 42%, followed by the UK and France with 25 to 34% and 25 to 28%, respectively. For the future projections, it was studied the increase in the energy recovery potential in Europe based on the population progression to 2030 and 2050, with results showing an increase of almost 9% of the total potential for micro-hydropower. These results show an important potential for micro-hydropower in the water industry to generate clean energy and contribute reducing the energy cost and emissions linked to the water sector. However, the more detailed information that can be obtained from the different organizations and companies and a closer collaboration with them could help to improve the level of detail in the results. Of course, although several assumptions have been necessary, the results obtained in the different developed studies prove that the role of micro-hydropower can make a valuable contribution to improve the sustainability of the water sector. And that's all for me. Thank you very much for your attention.
Thank you, Aida. I will reserve the questions and answers to the end of both presentations, if you don't mind. Now we will start with the presentation of Indalecio.
Good afternoon, everybody. During my presentation, I would like to present you the benefits that are associated with the installation of micro-hydraulic power plants in water networks. These benefits are not only economic benefits, but also others like environmental or improvement in the management of the networks. This is what we have tried to assess in the REDAWN project. The most benefit that would take place if we were able to take advantage of the energy potential identified into the water networks of the Atlantic area. I will start my presentation with an introduction of my organization, the Fundación Asturiana de Energía, and then I will try to explain some general features about the studies that we have carried out in the framework of the REDAWN project, and then I will present the main results of each study. I will start with the environmental impact assessment study. Then I will present the economic and feasibility assessment study. And finally, I will present the results of the sector-level economic impact analysis. Finally, I will try to give some conclusions, general conclusions, about the work that we have carried out with the elaboration of these studies. First of all, let me present the Asturian Energy Foundation, FAN. We are the Regional Energy Agency of Asturias, that is a region that is in the north of Spain. And our main objective is to improve the sustainability of the regional energy model, which is key in the recent years, as we are now in an energy transition process. To achieve this, we are developing several activities. We are advisor on energy issues of the regional and local public authorities. We carry out energy studies at regional level. We act as an innovation support entity facilitating the implementation of technological demonstration projects in the field of renewable energies and energy efficiency. We coordinate the regional energy cluster of nearly 50 companies. We carry out increasing awareness campaigns, training, information and dissemination activities on energy issues. And finally, we also participate in renewable energy promotion projects of interest for the region. In this way, we are investors in wind farms, in mini hydraulic or micro hydraulic plants, in photovoltaic plants, or even in a pellet factory. As part of these activities, we joined the consortium that is carrying out the REDAWN project. Our main activities of finding the project are being the installation and operation of a pilot plant in Spain that is located in Palmería in Córdoba, and the assessment of the benefits of this installation. I must say that this analysis has been carried out with the collaboration of ICT, I mean the Superior Technical Institute of Lisbon and the Trinity College of Dublin. This assessment has been summarized into 3 studies, one about the environmental impact assessment, other about the economic feasibility study, and a third one about the sector scale economic impact analysis. These studies have 2 clear objectives. First, present the REDAWN project results, and and second, provide to potential developers with information for their decision-making activities. The scope of this study is in the Atlantic area, what means the whole country of Ireland and Portugal, and the Atlantic face of United Kingdom, France, and Spain, the regions that are green in the slide. In this area, it has been considered the same water networks in which the energy potential presented in the previous intervention has been quantified. These are the wastewater networks, both urban and industrial, including, of course, as main energy demanding installations, treatment plants, the drinking water supply networks, including as main energy demanding installation, the potabilization plants, and the irrigation systems that are located in the warmest regions, mainly Spain and Portugal. Related to the environmental effects analysis, this study has 2 different parts. The first one considers the main environmental impact caused by the operation and maintenance of a micro-hydraulic plant in water networks. Related to this, the main activities that can cause some environmental impacts are: first, power consumption. what means CO2 emissions and other greenhouse gases emissions associated with the production and transport of electricity. Indirectly, the associated electrical grids cause electromagnetic pollution problems, risk of bird electrocution. Second, the maintenance tasks. In this case, the environmental effects considered are risk of soil and water contamination from accidental spill or inadequate waste management. Finally, in the operation of the water networks, there is the risk of pipe leakage. In this case, the environmental effect considered are the potential modification of soil and groundwater conditions. Among them, the most important environmental impact is the one associated with energy consumption, since the rest is due to accidental or extraordinary situation. That is why our studies have been focused on this aspect, in the electrical consumption and its greenhouse gas emission associated. The second part of the document is an assessment of the potential environmental benefits that could result from the integration of this device, of this technology in the water networks. The study includes the commissioning and operation phases. Considering a massive installation of these plants in the optimal sites that we have identified, we could achieve first, a reduction of the greenhouse emissions associated with the electricity generation due to a lower grid power consumption. Additionally, we will contribute to implement a more distributed generation energy model, which would reduce all impacts associated with the transport of electricity. We must take into account that we will achieve this without alteration in the physical chemical properties of the circulating water. Second, other positive environmental effect to consider is the reduction of the risk of soil saturation from pipe leakage, because this technology works as a pressure reducing element. To quantify in some way these benefits, we have estimated the potential in the reduction of CO2 emissions using the consumption of electricity. Considering the average emissions of each country in the generation of electricity, it's possible with the energy consumption to estimate the carbon footprint of water networks in the Atlantic area. Considering the energy reduction potential calculated in the study presented before, it has been possible to estimate the CO2 emission savings achieved through the use of these facilities. The graph on the left shows the electrical consumption and its associated emission for the water networks in the Atlantic area. As you can see, the total CO2 emissions in these networks are 1.8 million tons of CO2 per year. The highest emissions are in the wastewater networks, because this system has the highest consumption of electricity. And in the other side, irrigation sector has the lowest emission rates, with only 7% of the total emissions. The graph on the right shows the estimates made on reducing the carbon footprint with the use of the identified micro-hydroelectric plants potential. It had been identified a total emission reduction potential of more than 0.2 million tons of CO2 per year, saving more than 12% over those 1.8 million tons per year. By sector, the greatest reduction potential is identified in irrigation system, with the 53%, and the lowest potential is identified in the wastewater networks, with only 2%. In distribution by country or regions, the highest potential of reduction is identified in the Atlantic area of Spain, with a potential of 26%. due to the significant number of sites identified for the installation of this technology in the irrigation facilities. At the other end is Ireland, with only a potential of reduction of the 4% due to less locations identified. Related to the second study, the economic feasibility study, we have divided the study also in two different parts. The first one is a description of the condition affecting the economic viability of a micro-hydroelectric plant. As in other economic analysis, it has to be based on an income-cost balance to maximize a profit and shorten the depreciation period of the investment. The main income identified is due to the generated electricity that can be sold to the grid or used as self-consumption. As can be seen in the chart of the right, which show the average prices of the electricity market for generation and consumption in the country of the Atlantic area, the values of the first one are obviously always lower than the second ones. So the most economically advantageous strategy in all countries is the self-consumption. In order to maximize the generation of electricity, and in this way, the incomes, the main parameters to consider are, first, the hydraulic resource available, what is defined by the heat and flow in each location. And second, the efficiency of the plant, what depends on the available technology. In this case, the hydraulic turbine is a key element. There are several models like Kaplan, Pelton, Francis, and in our project we are using the PATS or power works as turbine. Regard to the cost, on one hand, there are the initial investment costs estimated annually in the depreciation item, and on the other hand, there are the costs due to the operation and maintenance tasks. With regard to the operation, most of the systems are remote control and do not require a specific personnel for the work. So in our assessment, we have considered only maintenance costs. The second part of the document explains the economic benefits resulting from the integration of micro-hydroelectric plants into the water networks. The most important identified are, first, the reduction of energy costs. Following the self-consumption strategy, it's possible to reduce our energy consumption and in this way, our energy costs. Second, the reduction of investment costs in reducing pressure valves or similar equipment, because these micro-hydroelectric plants indirectly act as or work as water pressure reducing elements. And finally, the possibility of reduction of operating costs. And the electrification of water networks in isolated areas, combining with the use of sensor and monitoring remote control device, allows us to improve tasks as leak detection, pressure regulation, or reading water quality parameters. It would have an impact on greater efficiency in water and energy consumption, and in this way, an optimization of operating cost. By countries or regions, the highest potential appears in the Atlantic area of Spain, with a potential reduction of 27% due to the significant number of locations identified. And at the other edge, Ireland, with only 4%, presents the lowest potential. Finally, regarding the study of the effect on the water sector, a first assessment of the situation of each sector has been carried out per country. In this way, it has been considered several representative indicators to evaluate the situation in each sector. In the case of the water treatment, it has been considered the water productivity. In the case of irrigation, the volume of water. In the case of water purification sector, the volume of wastewater generated. And in the case of industrial water, the volume of water consumed by the industries. Once this first assessment was carried out, the benefits provided by the micro-hydraulic installation in the sector were presented in a qualitative manner. This way, it's observed that these benefits can be summarized in three. First, the environmental and economic benefits already explained in the previous slides. Second, the electrification of hydraulic networks that allows the modernization of the equipment, the use of sensor, and with it, the improvement in the management of them. With electrification, you can do rate control of potential leaks, as well as install devices to improve water quality in locations where now there is no agreed supply. Finally, consideration should also be given to the positive image for the sector, that it can show technological renewal aligned with the European strategies, like, for example, the Green Deal. In a quantitative manner, to get an idea of the size of the water sector, in the slide is shown the water use of each sector per year. It's observed that the sector that moves the highest volume of water in the Atlantic area are the wastewater treatment networks, and the least, the purification water treatment sector. By countries, Spain is the one who moves a greater volume of water, when Ireland moves the least. As for the potential for the implementation of micro-hydraulic technology in the water networks, it's not that the greatest potential in the water sector is in the UK, and the less potential is in Ireland. Finally, I would like to point out some reflection on the possibilities for implementation of micro-hydroelectric plants in the water networks. First, is not that in the water sector there is a trend of increasing consumption of energy due to a higher degree of purification, a higher water quality requirements, and for the use of technology that require greater energy consumption. In this context, the use of micro-hydroelectric devices at points where there is a water excess pressure allows not only to help to reduce the problems of excess water pressure, but also to reduce the carbon footprint associated with the sector and reduce its operating costs, and at the same time that it's possible to improve the management of the network. To give us an idea of the potential effect that the use of this technology can have on the sector, it's estimated that it can be reduced by more than 10%, both the associated CO2 emissions and the energy cost. All the results and conclusions can be found in 3 documents that are hosted in the publication section of the project website. And that's all. Thank you for your attention, and I hope that you find interesting these results. And now I remain at your disposal for any question or clarification. Thank you.
Thank you to the speakers. Now we'll enter in the discussion with questions and answers. We have now already one interesting question from Paulo Branco. Paulo Branco is professor in the electrical and computer department at the IST with 2 interesting questions. One is about, was the estimated potential power computed before or after the PET? Hydraulic plus electric generator, okay? Having a combined efficiency. So it is important, this question, in terms of the estimation of the available power that we can install in the water networks. If you are considering the combination of efficiencies from the hydraulic mechanical and the electric efficiencies? This is one question for the subject of Aida. Another question is if, depending on the power at play, the hydraulic turbine and the electric generator can change substantially its efficiency. The experience of Paulo Branco here, it's very interesting because in some cases we can try to estimate a power installation for a specific water network, and after the implementation, maybe the power generator is much lesser, okay? It is very interesting to clarify this subject. I'm not sure if I want to explain this,
Yes.
or any other colleagues from this part of the work.
Okay, I would like to say something. I think that I can answer both questions at the same time because both are related with the efficiency and the pump and the motor and the pad. In this case, we have considered a global efficiency for both, a total efficiency. And as you have seen in the presentation, we are working with a very at a wide scale with several countries, 4 sectors. So with a lot of different frequency records. So in this case, as we are trying to find global results for the potential energy recovery at a big area, we consider a conservative value, in this case around the 50%. And of course, I think that if we want more detailed results, we need also more detailed information. In this case, for example, for the wastewater treatment plants, we only had an annual average of the flow. So, of course, if the flow change, if the head pressure change, the efficiency is going also to change. But for a very big assessment as this one, we have to take some global values, as it is the case for the efficiency. And in this case, we consider that the results are conservative because we have considered a conservative value for the efficiency. But of course, a more detailed study for each installation will have more specific results.
Right. I can complement a little more because it also depends on the scale effects. Okay, if you are considering or making some tests in a quite small PET, pump as a turbine, of course, this will influence so much the total or global efficiency. If you are speaking in powers greater than 2 kilowatts, these scale effects can be a little more dissipated. So in an estimation, we have some hydraulic considerations, imposing some efficiency for the hydraulic system, okay? And of course, the efficiency of around 50%, in some cases can be lower, in other cases can be higher. I think it is a good point for an estimation in big areas for powers greater than 2 kilowatts. Thank you, Aida. I hope we clarify this a little better. Another question comes from Pradiumna, okay, and requests some clarification points, like as one. Why do we say recovery of energy? Okay, where was the energy lost if the initial system was not designed for energy generation? Okay, I can reply this because in these cases, most of the systems need to control the excess of pressure. So we use pressure reducing valves. As I make in my presentation, I mentioned this. Most of the water networks need to control the excess of pressure to avoid leakage, high levels of leakage, or even rupture of the pipe systems. We use the pressure reducing valves, so we drop pressure or in our energy flow. So we are telling with these studies that we can replace this effect by using energy recovery of these effects, okay, by using a pump as a turbine, for example. The second question is about if a water distribution pipe system is utilized for power generation, the project may be synchronous with the head losses designed for the distribution system. Every new microturbine to be installed in an existing system will introduce head losses in the distribution system. How significant are these head losses in total to impact the distribution system? I think this answer is correlated to what I said before, okay? We had some pressure reducing valves, we are dissipating the excess of energy, because it is important in some periods of our day, we have the flow variation, of course, will induce different head losses in our hydraulic system. In some cases, we need to control this excess of pressure, so we can make this energy recovery, replacing this effect by a turbine. Another question is about what is the plant capacity factor, load factor, achieved in these plants. Okay, load factor, maybe we are talking about the electric component, okay? In this part, we are analyzing or making an estimation based on the hydraulic data collection that we have. We imposed the typical load factor when we are passing from the mechanical power to the electric power. I don't know if any other colleagues can say more about this.
I think this question is related with the previous that we have discussed about also the efficiency.
Yes, in terms of the generator, of course.
Yeah.
In question 5, what are the types of microturbines? Are they vendor specific or standard turbines duly verified by the various govs, okay, and the stakeholders involved? Well, in this question, we made a search of available micro-hydros, and there aren't so much micro-hydros that can be applied in this micro scale. Okay, so we focused a big part of our study using pump as a turbine. Why? Because we have in the market a lot of type of pumps for different specific speeds, for different characteristics, okay, in terms of head, available head, and in terms of flow. So it was easier and cheaper to use this type of solution, okay, applied to water networks in this scale. For a bigger scale, of course, we have conventional turbines that we can use, for example, in small or in large facilities. But in these facilities that we are considering, most of the times the best solution is that we obtained using a pump working as a turbine. Even without any type of regulation, we can make some regulation, electric regulation and hydraulic regulation, or both, in order to control and to get the best energy or the best power conditions. Well, another question comes from São Paulo in Brazil. And the question is there any evaluation on how the optimization with the implementation of PETs other than energy can also prevent the network losses? Okay, when we are replacing a PRV by a PV, okay, or putting in series both, okay, both devices, in the optimization that you developed, Aida, did you analyze the prevent of the network losses associated with this in terms of excess of energy that we need to control, or in terms of water leakage? Okay, if you control the pressure, we are also controlling the water leakage. Okay, and there is the possibility that the financial impact of this optimization is greater than the energy production. Yes, that's true, but in some locals, when you don't have any energy available to put this type of devices, it is a very interesting solution and can solve our problem to transport energy lines until that place. For example, most of these devices, in terms of the energy productions, we are considering a standalone solution. Standalone solution normally in rural or in isolated zones. Whenever we have maybe only a fuel generator, okay, generating a lot of pollution and other environmental associated impacts, putting this, for example, in the irrigation network, in the pilot demonstration developed in Spain, in the irrigation network, we replaced a fuel generator by a pump working as a turbine. It was a great solution in terms of different type of benefits associated, okay? Any more question? Okay. If there is no more question, I hope we clarify some issues here. I'd like to thank you very much for, in particular for the speakers, Aida and Indalecio. They bring us a lot of work developed in this both work package 4 and work package 5, with interesting results. Thank you also to all of the interested in this project, okay, to all the attendees and the participators, okay. We also had another important component already covered in the 2 previous webinars that we can find on the REDAWN project website. Okay, now I'm closing the section, sending my best wishes to all of you, and we'll keep in touch for the final webinar that will take place on February, as we can see here. Save this date for 9 February 21. And we hope to see you there with these enthusiastic questions and discussions. Thank you very much for all of you.
Thank you.
Thank you. Thank you very much.